Okay, so this says the surface charge density on a long straight metallic pipe is sigma. Okay. Assume the pipe diameter is 2a. So they're saying that this radius is a, and the surface charge density is sigma, meaning per unit area you have a charge of sigma. Okay. What we'll need to do is we'll need to find the linear charge density, how much charge there is per meter. Okay. And let's first do that. So the linear charge density is okay. So what? So imagine a cylinder on it of unit length, and the question is how much charge there is there. Okay. So lambda would be sigma times the area of that unit cylinder, and that unit cylinder is oops. Here is 2, a is the radius, so 2 pi a times 1 meter. Okay, so it would be sigma times 2 pi a, that's the circumference of the circle, times the height 1 meter. So lambda is 2 pi sigma a. Alright, here's why we did that. What is the electric potential outside and inside the pipe? Assume the pipe has a diameter. Okay. So you guys know that from a linear charge density, the electric field is pointing out like that, and the magnitude of the electric field is given by 2k lambda, the linear charge density which we found, divided by r. So the electric field is given by that. Okay. All right. So now let's. What we'll do is we'll take a top view. Let's do a top view. So here's the pipe. Here's the electric field. It's pointing radially out. And what we'll do is we'll find the. So we know that V is high here and V is low in that direction. Electric field point in the direction of. Oops. Electric fields point in the direction of decreasing potential. Okay. So what we'll do is we'll find the potential difference between 2 points here. Okay. And we'll call this rho 1, this distance rho 1, this distance, and they're all measured from the center of the pipe, rho 2. Okay. So let me relabel this. We'll call this V1, V2. Yeah. All right, so check your notes. V2 minus V1 is again minus V2 minus V1 is negative of this line integral. Okay. So we are going to take the line integral and our path is going to be this, from here to there, radially outwards. All right, so negative rho 1 to rho 2. The electric field is 2k lambda divided by rho hat d rho hat. Okay. Here's the electric field, this is ds. Okay. And I'm going to go over here since I have enough space. V2 minus V1 equal to minus 2k lambda is a constant, d rho by rho rho 1 to rho 2. So there is the potential difference between those 2 points. As already mentioned, so V1 is at a higher potential, V2 is at a lower potential. V2 minus V1 should be negative. There's the negative sign. All these guys are positive. And this guy is positive too. Rho 2 is bigger than rho 1. Okay? So you see V2 is less than V1. Okay? Now they ask you, so let me, so now I'm going to blow up this diagram. So you know, now we know the potential in this region outside. Okay, we know the potential difference between any 2 points. This would be rho 1, this would be rho 2. Well, let's say this is rho 2. We know the potential difference between these 2 points, which is given by this expression. Okay. Now what they're asking you is, so you know the potential at, okay, so now what they're asking you is, what is the potential inside here? This is a conductor. What is the electric field inside here? I'm sorry? 0. The electric field inside is 0. So let's do the following. So let's take rho 1 prime, this is rho 2 prime. Okay, so V2 prime minus V1 prime equal to minus 2k lambda, oh no, not, minus E dot ds. Okay, so you take any path from these 2 points, what is the value of this integral? E is 0, so this integral will be 0. Okay. So what we are saying is, this is 0, the potential at any point inside is the same as what's on the surface. Okay, so the potential any point inside is equal to the potential at the surface. Okay, so that's, so, and that's true generally of a conductor. Inside a conductor, the potential is the same as the surface.